Speakers of Francesco Russo, and he's going to talk about stochastic calculus for regularization in Banach spaces and applications.
Thank you very much to the chairman, and thank you very much to the organizers to give me the opportunity to come again to this very nice and very prestigious place. So, as we mentioned, so this is it continues the approach of stochastic calculus regularization developed in finite dimension by Pierre Valois and myself, and continued by several other authors. And this includes joint work with Cristina Di Girolami, who is in Le Mans, and Giorgio Fabbri. So, in fact, just some related references. So, essentially here there are two directions which are developed, two applications, one which goes in the case where B is the space of continuous functions on minus tau 0, and the one which is maybe more traditional to which consider applications to SPDs with value in a separable Hilbert space. In both cases, I mean, this approach brings, in my opinion, something. So the work with Di Girolami concerns essentially the B equal the space of continuous function in minus tau 0, and the work with Fabbri, the work about SPD. So it's a verification theorem concerning SPDs with our approach. But so in fact, so these are the former finite dimensional approach concerning stochastic calculus regularization. So in fact, I start with the motivation which comes from the space B equals C minus tau 0, in fact. So which concerns, in fact, which is motivated by a one-dimensional problem, essentially. So if you consider a classical Brownian motion, so you will go back to very fundamental calculus. If you have a classical Brownian motion, it has the property that the quadratic variation equals t. And you can represent, through Martingale representation theorem, every square integrable random variable by the expectation plus integral 0 to t xcs dws, where the integral is in fact a Ito integral. So essentially a deterministic F0 measurable, if you want, random variable plus an integral of a progressively measurable process with respect to the underlying, which is Brownian motion. If H is in D12, you can express this using the famous Clark-Ocon formula, and in that case, the process Xi can be represented through the conditional expectation of the Malyaven derivative SH given Fs. So I write dm in order to distinguish to the classical Frechet derivative later. Okay, so now the question is, we have, instead of supposing that the underlying process is distributed according to the Wiener measure as Brownian motion is, so we try to see if there is some robustness with respect to if you give up to the law and you conserve the property of finite quadratic variation. You consider a process of the same quadratic variation, but which can be completely distributed in a very different way. And in that case, you can ask you about the robustness of the Clark-Ocon formula in some sense. And in that case, of course, you have to interpret the integral here. And one way to interpret the integral is, for instance, to consider as a limit of progressive Riemann sums. For instance, we will propose another way, which is, in our opinion, more operational, but it's not the main point. Okay, the class of finite quadratic variation process is very rich, in fact. So it goes much beyond the class of semi-martingales. And and many people have worked now recently, for instance, for with respect to fractional Brownian motion or processes of multifractal type. But there are many other classes of finite quadratic variation process which have a finite quadratic variation. And one of them, I don't mention the class, how rich is the class, but I can discuss with you later. But of course, one of the most famous are the Dirichlet processes that I call Fermat-Dirichlet process because he introduced them as the sum of martingale plus a zero quadratic variation process. Again, you can consider this as, for instance, by limit of sum of square of increments. But also you can find processes which are really finite quadratic variation and they are not Dirichlet. There are such class. An extension that we introduced in the purpose of generalizing Ito formulae, it was the notion of weak Dirichlet process, which plays an important role in the class of generalized Ito formulae, is instead of having a local martingale plus zero quadratic variation, so you have local martingale plus a process which is orthogonal to any martingale with respect to the fixed filtration. And this is also a very useful tool. It has been applied also in control theory, because since this decomposition is unique, and you can try to see, so one of the important results of Fermat was that the processes which are Dirichlet, Fermat and Berthoin, Dirichlet, they remain Dirichlet if you apply a C1 function. Now, very often, if you have a time inhomogeneous function, depending on time and space, if the dependence on time is minimal, for instance, continuous, you can ask, if you start with a finite quadratic variation process, you transform it in a process which has infinite variation, but still it has some property of that type. So a C01 function of a Dirichlet is weak Dirichlet. A C01 function of weak Dirichlet, if it has finite quadratic variation, it is weak Dirichlet. Okay, so this is, in fact, in order to consider an underlying process which is one-dimensional finite quadratic variation. And as I said, one of the spaces, C minus T0, is motivated by looking, for instance, a path-dependent random variable. If you want to represent a function which depends only on the last point of the underlying, it's relatively easy. You have to solve a PDE, a parabolic PDE, relatively simple. But if you have path dependency, then one possibility, is not the only one, is to consider an evolution in such a space. And we call associated with a one-dimensional process, we associate a window process which is a C minus tau 0 valued stochastic process. This is a natural association. Okay, now the problem could be to represent a functional which is defined on C minus T0 on R, which has some minimal regularity with respect to this. If you are X is Brownian motion, the result is well known. You have Clark-Occon formula, generalization of Clark-Occon formula. And if you don't have the property of Wiener measure law, then you can only use analytical methods and not probabilistic methods. Okay. Yeah. Here a continuous process, yes, yes, for class. For the calculus, you can consider also jump processes, but for this application, yes. So now the idea is to consider it as the final value of a C12, if you have enough regularity, let's say, C12 0t cross C minus T0 function, which solves some infinite dimensional PDE. So this is the idea behind. And So in fact, you have to work, in order to treat a one-dimensional problem, you transfer it in an infinite-dimensional problem. But in that case, the type of integral that you have has to be reinterpreted, for instance, by some limit of progressive Riemann sums or other ways. And in that case, the process psi will be the d delta 0 u of s xs point. So this is the projection of the Frechet derivative on the delta 0. Okay, now let's come back. As I said, in fact, instead of using discretizations, we could use discretization. We work with regularization because for many aspects it is more general, and for instance, it extends classical Ito integral and also more operational. So now, if you come back to the if you don't have any property of semi-martingales, one possibility to define stochastic integral is to define it as the limit of this type. So in fact, you regularize the derivative in a forward way, and this gives you forward integral.
The left-hand side is not necessarily continuous because the zero.
Yes, so exactly. You have to ask that there is a continuous version. In fact, this is at the beginning we worked with UCP topology, and finally we found that it was a bit restrictive. So we defined as it exists in every T, and there is a continuous version.
Take the full limit as that sign goes to 0?
Yes. And for the bracket, so this was introduced by us in 91. For the bracket, you have something similar, but then the relation between, if you have x equal y, the relation between UCP and probability is almost immediate by Dini type lemma.
So you take only limit from the right, yes?
You can also take the limit from the left for this. This is equivalent. For the integral, not. But for the bracket, it's equivalent. So if xx exists, then you say that it has finite quadratic variation. And of course, the integral, when you have a good semi-martingale, for instance, let's take a Brownian motion, y, if it's Ito integrable, then the forward integral exists and it equals Ito integral. The covariation generalizes the classical covariation. Okay, now one very famous theorem of Fermat, which was revisited by us and extended, is that if you have a finite quadratic variation process, then this integral, and f is C12, this integral exists and it equals this. So you have what you expect as a Ito formula. And okay, now just to put a list of people who contributed to the calculus V regularization. I asked myself, in fact, there are several people who worked on this subject since the beginning. Now let's go try to do infinite dimensional approach. And let's fix a separable Banach space, and X a b-valued process, and you take F of C2 type, Frechet. Okay, so now if you try to write such a formula, so you will laugh, because of course it cannot work like this. Even if you take, of course, no, it works in some cases, but very special cases. It works, for instance, in the framework of Métivier-Pellomail, Dincoleanu, and so in that case, in fact, they consider such, maybe it's worth that I write it here, they consider some type of quadratic variation, which is, in fact, you have so Métivier-Pellomail, for instance. If you have a process, X, Banach valued, then you have the scalar quadratic variation. They call it the real. It's limit when epsilon goes to 0. So in fact, I retranslate in terms of epsilon, even if they use the discretization, but it's essentially the same. So then you have xs epsilon minus xs square ds, and you have the tensor quadratic variation, which is the limit when epsilon goes to 0 of 1 over epsilon integral 0 to t xs plus epsilon minus xs tensor product 2. So you have a tensor, and so this belongs in H cross H with any topology, but you can we will work here with the projective topology, which is in fact the one which makes equivalent or isomorphic to the space of bilinear continuous functions. Okay. And they consider a strong convergence in this space, essentially. And okay, this is in fact is very nice, but it doesn't work in most of the cases. Okay, now if I try to, of course, let's imagine I would like to try to prove such a formula. So I consider f of x. We will see that, for instance, the window-Brownian motion has no quadratic variation in this sense, but it has a chi quadratic variation for a class of spaces. And okay, the definition is this. You consider first an epsilon regularization. Before here we had B cross B, and here you have B cross B star. Now we have chi, and chi star. So this is a fundamental approximation, sorry. So unfortunately I'm on the movie like this. But okay, x is a chi quadratic variation if the first condition is fulfilled. This is the condition of scalar quadratic variation. We consider norm chi star here. And the H2 is more related to the tensor quadratic variation. And for every phi in chi, you have that x epsilon phi converges UCP to x phi for every phi in chi. And then there is another small condition which requires that you have a good version as a chi star valued process. And if chi is separable, the H3 is automatically satisfied. So you in fact, what we call the quadratic variation is this chi star valued process, chi tilde, x tilde. Okay, if in some sense we call global quadratic variation when chi equal to full space, but even in that case it's more general than this, in fact. So if you have such a notion, you have a global quadratic variation. The global quadratic variation is related to a weak star convergence, in fact, because the process at the limit, it may live in the bidual. So the global quadratic variation is B cross B star star valued. Okay, this extends, of course, the case of n-dimensional. If you have a vector which has all the mutual brackets, then you have a matrix, and this matrix gives you our global quadratic variation x tilde. The case of which appears in the book of the Bartosz-Zarczyk, for instance, they use a language of operator. I retranslate in the term, so they have L1H. I retranslate in the term of tensor product, and in that case, it's their bracket is an object which lives here, and such that if I take a tensor product of the type A star cross by star, where A and B are in H, I put the star by the association in H star by Ritz theorem, then you get that this evaluation gives you the classical covariation of MA and MB. So this in this case, M has a global quadratic variation. And as I said, this case also is a particular case of the global quadratic variation. In that case, you can write infinite dimensional Ito formula. You suppose that F0T cross B in R is C12, the process has a chi quadratic variation, and the second derivative lives in chi. In that case, the forward integral exists, and the following Ito formula holds, as you expect. Okay, now another type of, in fact, the first idea of considering the first idea that can come in mind for chi is not really the sophisticated chi that you have in C minus pi 0, but if you consider U0 and U1 some Banach subspaces of B star, if you take the product here, the projective tensor product is a chi subspace, which is not the full space. So for instance, if you take a semigroup, a generator of C0 semigroup ST, so if you think in the spirit of mild solution of SPDE, then W is a Q-inner process, and you consider some sigma which are predictable with, in the good sense, with value in L2 U0 H, B with value in H, such that you have this condition. Then a convolution type process, so you are very familiar about this, of course, much more than me. And it's a process of this type, which in fact extends the notion of Ito process from one dimension. And if you write nu0 equal dA star, and chi equal the tensor product of this, then you can show that you have a finite quadratic variation. If not, of course you don't have, because if 0 generally is outside the domain. So in that case, you can write a result like this. Such a convolution type process can be decomposed in a martingale part plus a part which is bounded variation plus a process of this type. So that a t phi is equal to 0 to t excess a star phi ds for every phi in d star, and v as chi quadratic variation. So in fact, you revisit the notion of mild solutions of convolution type semigroup through the notion of quadratic variation, but you relax the notion of quadratic variation. And so X is a chi quadratic variation, which is only given by the restriction of the quadratic variation of the martingale to chi. And I was mentioning the result one-dimensional about Wigg-Dirichlet. An important substitute of Ito formula in that case, of course you can write, I don't mention, a Ito formula of class C12, which is also relatively interesting, which in that framework you go behind your chi, but the transformation of C01 type are really the true substitute of Ito formula for functions which have very few regularity, like a Fukushima, generalized Fukushima decomposition, for instance. So in that case, you have mt is equal u0 x0 plus 0t dx us xs sigma s ws plus a term which is orthogonal but in infinite dimensional sense. So in our sense, so we introduce the notion of quadratic variation, but also you can extend in the notion of covariation. So and this helps you for making calculation, for instance, for verification theorems in control. Now let's come back to window process. Window process are processes with value in B. Let's take X a continuous real value process, X dot the window. Of course, there are situations in which everything goes well. I mean, if you take a Hölder continuous process, like fractional Brownian motion for gamma bigger than 1/2, or bifractional or multifractional, you have always a global quadratic variation. So the quadratic variation is 0 in the strong sense here, even in this sense. If you take Brownian motion, then you don't have global quadratic variation, and you have also many situations. This is a process which is not Dirichlet, and it has the same quadratic variation of Brownian motion for some parameter h and k. Now, the family of chi subspace in that case that you can use, typical L2 of minus tau 0 square, the multiple of Dirac's, or you can also add the key subspaces. You get still a key subspace. So they are not always of product type. And you can also have a space which is of diagonal type, which are measures concentrated on the diagonal but absolutely continuous, with density absolutely continuous. This also gives example of chi subspace for which you have the Brownian motion and the processes which has the same quadratic variation as Brownian motion have a good chi quadratic variation. So at that point, the generalization of Clark-Ocon, as I said, we want to represent h is equal h of xt dot, like this, and as the endpoint of t of a function evaluated in capital T and xt. So now the PDE that we consider is of that type, in fact. You have dtu plus, here you have a term that you have to give a sense, and you give a sense in several cases. For instance, when eta, when this is the absolutely continuous part of the derivative of u, if this is, it has a density and it has bounded variation, then this makes sense. Or if it has Hölder continuous, by making use of Young integrals and so on, it can also give sense.
What do you mean by this bracket?
Which bracket?
The last one, this one.
This is, in fact, this d2u is a measure, and it's integrated on dt, in fact. So this is a measure on the diagonal. It evaluates only the diagonal. And the diagonal is, yes, it's this one. And the first integral is defined by integration by parts. So this is one possibility of PDE. In that case, if you have a solution of that PDE, then you can write your representation like this. So in fact, you can, the first idea is to try to find such a functional, and then to apply Ito formula that we have, and this says essentially that if you have such a solution, then so a typical theorem is this one. There are other representation theorems, but if you have H from B to R, such that you have U in C1, 2, 0T cross B intersection C0, 0T cross B, if X is bound on dA C X U T eta is bounded variation for all T and eta, and the second derivative lives in this space, so the direct sum of d0 plus L2, this the multiple of direct measure, the square plus the diagonal space. Then if you have this, then you have the representation. And if U solves this, then you have the representation. This includes also the case sigma equals 0. And you can also have sigma dependent on x and so on. I'm really concentrating on the most simple case. And then, of course, if you have such a function, everything is fine. The most difficult thing is to construct such functions. And for instance, you can construct them when you have enough regularity with respect to L2 minus T0 plus delta 0. But in some cases, you also, if you have a finitely based final condition, you can have even f only measurable, but phi1 until phi(n) C2. Of course, this because we are not in the Brownian framework. We are in a more general framework. We have processes which have the same quadratic variation as Brownian motion. And in that case, also you can find situations in which the terminal value is not even in L1. Exactly. So this is an alternative approach which was developed parallelly by Ramaconte and David Fournier using the Dupire derivative. And in fact, there are some similarities, there are some differences. I mean, in fact, the two objects are relatively different. The PDE that they get is they put together two of our terms. But okay, thank you very much for your patience.
Thank you very much. Are there any questions or comments?
So you can apply the ether formula to the convolution, as you
Yes.
showed. So how far can you get? So did you spell this out more?
Yes.
So semi-linear, multiplicative noise, and something like that?
So in fact, we consider a classical SPD. The difficulty, in fact, the difficulty doesn't come from the noise. The difficulty comes from the domain, in fact.
Yeah.
Yes. So in principle, in the cases where you can state a SPD in the sense of the Plato-Zapcik with sigma and B, Lipschitz and W, and you have the good conditions and so on, then you can use this machinery, in fact.
Can you have the notion of chi semi-martingale?
So in fact, we have a notion of chi Dirichlet.
Chi semi-martingale.
Yes, this I was trying to say. Sorry. No, we have chi Dirichlet, chi semi-martingale. It would be
More general than
in some sense, but I never thought about this. So I mean, it could be a process which we have a martingale plus a process which has a chi-1 variation, in fact. But I never thought about this, in fact. This, I don't know if... yes,
If you apply your Clarke cone to a finite dimensional semi-martingale, do you just get the usual one?
so if you apply, you get the usual one, provided that you have some small regularity, that you have to specify. Because here you only use analytical methods and not probabilistic methods. So in a dense class, you can find a dense class in general for which you have the same representation. But then the problem is that when you have the probability there, it helps you to prolongate. If you don't have the probability, you remain at analytical level. Like if you, I mean, for instance, if you continue, just the analogy is stupid, but if I have a function on R, if I think, if I say that it's continuous, I don't need to speak about versions and so on. But in general, so I mean, if you cannot get the same Ito formula for all cases, for all targets, but for a large class of targets which are dense and also some are path dependent, some are they depend only on a finite number of points and so on. But you can get a large a dense class.
So in this simple case, there's also the Comte Dupierre one you mentioned. Does yours look the same as that?
Yes, it looks the same, but in fact, in that case, they considered they were more interested in Brownian motion, essentially, and Dirichlet processes. It looks the same. In fact, they don't look the same because the partial derivative, the vertical derivative is the same, the d delta 0. The horizontal derivative, it's different because we work with a Frechet type derivative, and they really work on the path. So what they call the derivative of horizontal derivative is not really. So for us, it includes derivative with respect to time and an integral minus t to 0. This what we call the anticipated integral. So in fact, it's a strange derivative. This one. Our is Frechet. In their case, they have another approach. In fact.
Can you mentioned you can apply to stochastic convolutions. Can you give application of the result you get in this way?
Yeah, so in fact, we got the first result about, I don't know if you are familiar, maybe you saw a paper of Gozzi and myself about the stochastic control theory, verification for a stochastic control theory, stochastic control theorem, in which we had some solution of Hamilton-Jacobi which was irregular, but not that irregular as in the case of viscosity. So we had a C01 solution in that case. And in that case, one of specific tools was the fact that we could write U of t st, the diffusion process, as a martingale plus a process which has a zero covariation with respect to all martingales. This was the Wick-Dirichlet characterization. And then this coupling with other characterization, knowing that U was in some good domain, it gave a sort of Ito formula for irregular. And here we do this, in fact. We generalize this to this framework. So we use this C01 transformation of this convolution type process. We characterize them as a Wick-Dirichlet, and then we get two different representation, and we identify them, and gives us some verification theorem with conditions which are less regular than in the literature. Let's say this is the application we get. It's in the paper with Giorgio Fabri.
Any more questions? There is a thing like a mild Ito formula.
By Professor Rögen and Da Prato and so on.
Maybe, I mean, the last applications could also be obtained by this mild.
Once it could
directly
be
tailored to the stochastic convolution. I mean, to the idea that you subtract the stochastic convolution from the equation. So this is inside this.
I can imagine that
transformation in the state space, and it's. I mean, this you can prove.
In fact, we also. I remember that the first stage of your work at the beginning, Giuseppe, Professor Da Prato told me about one case, and it entered also in our framework. In fact, it was also interesting to compare. And in our case, the mild type Ito formula that we get in that case is that we can allow all the derivatives, not only in chi, but then the first derivative has to be in the domain of A star. This is our Ito formula that we get from our machinery, let's say. Then I have to say that I only knew the first very preliminary work, part of your work. I have to study more. Okay.
Not claiming.
No, but it's interesting.
Okay, any other question? If this is not the case, then thank you very much again.